We're going to look at Koch's snowflake curve, and this curve is interesting because it is a curve of infinite length but encloses a region of finite area. So to generate the curve, we start with an equilateral triangle whose sides have length, say, S, as we can see in curve C1 here. Then in the next iteration, each line segment is divided into 3 segments of equal length, and a new outward pointing equilateral triangle with its base removed is drawn, as we can see in curve C2. So this process continues recursively for every iteration, and we've got the first 4 iterations drawn out here. So C3 and C4 are also drawn. So what we're going to do in this video is we're going to find a formula for Ln, which is the length of the nth curve, Cn, and show that the limit as n tends to infinity of Ln is equal to infinity. So we'll start by finding the length of the first few curves or so and see if we can find a pattern. So the length of curve 1, which is going to be L1, well, we've just got 3 sides of equal length and the length is S of each side. So L1 is just going to equal 3S. So the length of each curve is going to be the number of sides that curve has times the length of each side of that curve. So we'll look then at the number of sides that each curve is going to have. At curve C1 we have 3 sides. Now if we look at curve C1, say this line segment here, well, in C2 we divide that into 3 equal line segments and form our equilateral triangle. So now we've got 1, 2, 3, 4 sides there, or 4 line segments. And that's going to be true of all the line segments from C1. So say if we take this one here, that now becomes 1, 2, 3, 4 line segments in C2, and this one here also becomes 1, 2, 3, 4 line segments. So that means curve C2, well, it's going to have 3 times 4 sides. And then for curve C3, we just continue that process on. So each time, we're going to have 4 times the number of sides of the previous iteration. So curve C3 will have 3 times 4 times 4, which equals 3 times 4 squared. And C4, well, it's going to equal 3 times 4 squared. And we just have 4 times the number of sides as C3. So multiply by 4, so we get 3 times 4 cubed. So we can see then that this indice here is going to be 1 less than the curve number, because each time we're multiplying the number of sides by 4, and we start multiplying 4 from curve number 2. That's the first time we do it. So in general then, the number of sides at curve Cn is going to equal 3 times 4 to the power of n minus 1. The other thing we can note is the length of each side at each iteration is going to be 1/3 the length of the sides of the previous iteration. So for example, if we look at curve 1, the side here, which is length S, well, in C2 we've divided that into 3 equal line segments. So that part here then is going to be S over 3, and this will be S over 3, S over 3, and S over 3. So that means then the length of C2, which is given by L2, is going to equal the number of sides at C2, which is 3 times 4, times the length of each side, which is S over 3. And then the length of L3, well, that's going to equal the number of sides at C3, which is 3 times 4 squared. And each side length is 1/3 the length of C2. So it's going to be 1/3 of S over 3. So simplifying that, we're going to get 3 times S times 4 over 3 all squared. So for curve 4, we can think of it this way. We can take the length of L3, so that's 3S times 4 over 3 all squared, and we've got 4 times the number of sides, so we multiply it by 4, but each side length is 1/3 the length of the previous iteration. So we times by 1 over 3, and simplifying that, we're going to get 3s times 4 over 3 cubed. So we can start seeing a pattern forming here. At each iteration of the curve, the length of the curve is increasing by a factor of 4 over 3. So that's because at each iteration we've got 4 times the number of sides of the previous iteration, and the length of each of those sides is 1/3 the length of the previous iteration. So that's why we're increasing the length of the curve each time by a factor of 4 over 3. So in general then, a formula for the length of the nth curve, Ln, is going to equal 3s times 4 over 3 to the power of n minus 1. So we can see from the lengths of the curves that we've already found that the number we raise 4 over 3 to is always 1 less than the curve number. So for example, when we were finding the length of the fourth curve, we raise that 4 over 3 to the power of 3, and finding the third curve, we're raising it to the power of 2, and so on. So as the length of our first curve was 3s, and then each iteration after that, we increase the length by a factor of 4 over 3, that's where we get our formula for the length of the nth curve as 3s times 4 over 3 to the power of n minus 1. So now we're going to show that the limit as n goes to infinity of Ln is equal to infinity. So we can start by noting that 4 over 3 to the power of n minus 1 is a geometric sequence with a common ratio r equals 4 over 3. And a geometric sequence is going to diverge if the absolute value of the common ratio is greater than 1. So in our case, the absolute value of 4 over 3, well, that's still just 4 over 3, because 4 over 3 is positive, and that's greater than 1. So we conclude then that the sequence 4 over 3 to the power of n minus 1 diverges. So what we have then is the limit as n goes to infinity of Ln. Well, that is going to equal the limit as n goes to infinity of 3s times 4 over 3 to the power of n minus 1. Now that 3s is not dependent on n, so we can take that outside the limit sign there. So then we get 3s times the limit as n goes to infinity of 4 over 3 to the power of n minus 1. So I've already shown that this part here is a geometric sequence that diverges. So that just means as n gets larger and larger, then that 4 over 3 to the power of n minus 1 is also just going to get larger and larger. So that means then that this 3s times the limit as n goes to infinity of 4 over 3 to the power of n minus 1 is going to equal infinity. So therefore we have then that the limit as n goes to infinity of Ln is equal to infinity, which is what we wanted to show. So as we do more and more iterations of Koch's snowflake curve, the perimeter is going to tend toward infinity.